Let me give you all the attendance link real quick here. 1 second. There you go. Get started here in a minute. Questions? Welcome, welcome. All right. All right, 110. Let's get going. We're talking about L'Hopital's rule. So here's the general statement of L'Hopital's rule. If f of x and g of x are both differentiable, then we can say the following. If the limit as x approaches a of f of x over g of x is either a 0 over 0 or an infinity over infinity indeterminate form. It doesn't matter what the sign of your infinities are. It could be a positive infinity over a positive. It could be a negative over a negative. It could be a positive over a negative or a negative over a positive. It just matters that it's something infinite over something infinite. So if your limit has one of these two indeterminate forms, then we can say the following. The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of x over the derivative of g of x. Provided that that limit actually exists. So this is only true if this limit actually exists. Provided this limit actually exists. Really, what I'm just saying with that is that if this limit ends up not existing, it's weird to say like the original limit equals a limit that doesn't exist. We would just say the original limit doesn't exist, but it's really not an issue that we typically run into. We're definitely not going to prove L'Hopital's rule because it's a bit complex, but we will kind of, I'll give you kind of, not an example necessarily, but kind of just some reasoning behind why it might be true. So let's look at this, not example, but reasoning. So why might this be true? Well, let's pretend that we have two cars traveling along. You've got car A, you draw a little car, kind of, that's a car, sure. So you've got car A here, and you've got car B down here. A drawing picture. And here's what we're going to say. The A of t is the distance or the position of car A. And a prime of t, the derivative of position or distance, is the velocity of car A. Similarly, b of t is the distance traveled by car B, and b prime of t is the velocity of car B. So here's the idea. Suppose both cars travel for an infinite amount of time, forever and ever and ever. But car A travels twice as far as car B. So suppose car A travels twice as far as car B for an infinite amount of time. What this would mean is that kind of no matter where you were in the time, car A would always be twice as far as car B. Or in other words, you could say that the limit as t approaches infinity of A of t over B of t is going to equal 2. Yeah, it's an infinity over infinity type because the distance is infinite, right? If you travel forever, you go an infinite distance. But the ratio of those infinities is that the top one is twice as big as the bottom one. But what does this mean about their velocities? Well, if both cars travel forever and car A goes twice as far as car B, it essentially means that car A had to have been driving twice as fast as car B the entire time. Or in other words, of course, I've run out of room at the most important part. This essentially means that car A's velocity, is twice car B's velocity. Or the limit as t approaches infinity of A prime of t for B prime of t is also 2. I know it's not like a perfect analogy, but that's the idea, is that if some limit of quantities that are both infinity, both 0, have some sort of limiting ratio, then their derivatives also have that limiting ratio. It might be easier to see this if you actually think about some actual functions. So for example, you could say that A of t, the position of car A, is 60t plus 5, where t is measured in hours and A of t is measured in miles. So A of 1 would be 65. After 1 hour, we've gone 65 miles. After 2 hours, we've gone 125 miles. After 3 hours, 185 miles. And so on forever and ever and ever. Which I know, right, doesn't really seem like, I know it's not realistic. Okay. And then similarly, you can say that B of t is something like 30t plus 20. We want to find the limit as t goes to infinity of A of t over B of t. That's an infinity over infinity type. The top is going to infinity. The bottom is also going to infinity. In the past, the way we would have dealt with this would have been by dividing everything by the highest power of t in the denominator. That's still valid here. You could totally do this as the limit as t goes to infinity of 60t over t plus 5 over t over 30t over t plus 20 over t. That's the limit as t goes to infinity of 60 plus 5 over t over 30 plus 20 over t. The 5 over t goes to 0, so the 20 over t, you get 60 over 30, which is 2. Or now, since it's an infinity over infinity indeterminate form, you could also use L'Hopital's rule. Yeah, oh, that's going to be equal to, let me write this way. The limit as t goes to infinity of 60t plus 5 over 30t plus 20 is equal to the limit as t goes to infinity of the derivative of 60t plus 5, which is 60, over the derivative of 30t plus 20, which is 30. The limit of a constant is just the constant. So that would also work. So that's the idea, kind of generally. Yeah.
So you take the derivative of both of them separately, you don't do a product.
Not product, well, right, you're not using the quotient rule at all, unless the top has a product or a quotient or a chain rule. But yeah, you're not taking the derivative of this whole entire fraction or quotient. Okay, let's look at some examples. And actually, let's look at two examples. We're looking at these examples. So here are two examples that you already know the answers to. The limit as x goes to infinity of 3x squared plus 5x plus 1 over 7x squared minus 2x plus 3. And I will first point out, this is an infinity over infinity type. The top is growing to infinity. The bottom is growing to infinity. And the bottom is growing to infinity, right? Because it's definitely an infinity minus a smaller infinity plus infinity. Plus 3, sorry. Everybody, I think, probably already knows what the answer to this is. What's the fractional answer that we will get here? Yeah, thank you. 3/7. And you could do this the normal way, or I should say the old way of dividing everything by x squared. You could even just say we know it's 3/7 because that was the shortcut, but we could also use L'Hopital's rule. When we use L'Hopital's rule, what I like to write above my equal sign is an L''H. There's still a limit there because we're still evaluating a limit. The derivative of the top is 6x plus 5. The derivative of the bottom is 14x minus 2. We still have an infinity over infinity type. So then we use L'Hopital's rule again. We get the limit as x goes to infinity of 6 over 14. The limit of a constant is the constant. So we get 6 over 14, which does reduce to 3 over 7. It also works for 0 over 0 types that we've seen before. For example, if I was going to take the limit as x approaches 6 of x squared minus 5x minus 6 over x squared minus 36, if we plug in 6, assuming I've done this correctly, we should get 0 over 0. Let's see, 36 minus 30 minus 6, yep, that's 0 over 0. And when you have a 0 over 0 type, that is also when we can use L'Hopital's rule. And I will point out, these are the only two types of things we can use L'Hopital's rule for. Anything else that's indeterminate, we have to manipulate before we can use L'Hopital's rule. It has to look like some sort of fraction that's either big number over a big number or 0 over a 0. Those are the only things it works for. So we could do this the old way and say it's equal to the limit as x approaches 6 and just factor. You get x minus 6 times x plus 1 on top over x minus 6 times x plus 6 on the bottom. And then you cancel those and you plug in for the rest and you get 7 over 12. Or you can use L'Hopital's rule and say the limit of this is going to be the limit as x approaches 6 of 2x minus 5 over 2x. Every time you use L'Hopital's rule, as soon as you've used L'Hopital's rule, that is when you should think about, can I plug in what x is approaching and get a real answer? If I plug in 6 right now, I get 2 times 6 minus 5 over 2 times 6. Definitely not 0 over 0. So that's my answer. 12 minus 5 over 12. Oh, it's the same as it should be. So L'Hopital's rule can be used for these limits we did before, where you could use algebraic methods or really most algebraic methods. But the point is, now we're going to see some limits where you can't have done what we did before. For example, something like the limit as x approaches infinity of x squared divided by e to the x. This is certainly an infinity over infinity type. So what do? Well, we use L'Hopital's rule. So using L'Hopital's rule, I get the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom, which is 2x over e to the x. And it's still an infinity over infinity type. 2 times infinity is infinity. E to the infinity is infinity. So I use L'Hopital's rule again. And I get the limit as x goes to infinity of 2 over e to the x. And now it's not an indeterminate form. It's not infinity over infinity or 0 over 0. If I plug in infinity, on top I've got 2. On the bottom I've got infinity. And 2 divided by infinity is 0. I will point out that sometimes people ask you to do this kind of argument to prove that an exponential function is always eventually bigger than x to any power. So in a similar way, you could show that e to the x is eventually larger than, say, x to the 100th power, or 1000th power, or 1 billionth power. It doesn't matter what the power is. Because if you keep doing this, like if that had been x to the 100th instead of x to the second, every time you take the derivative of the top, the power gets to be 1 less. Every time you take the derivative of the bottom, it doesn't change. So eventually, if you do this 100 times, you'll get to the place where the top is some constant and the bottom is e to the x. And even though the constant might be really big, e to the x is growing to infinity, whereas the constant is just some large number that's not infinite. And eventually that fraction gets closer and closer to 0. Kind of neat. Sure. Let's look at some other examples. Like the limit as x goes to infinity of the square root of x over the natural log of x. Whenever you're looking at a limit like this, you should always be asking yourself, can I use L'Hopital's rule? Then you might also ask yourself, should I use L'Hopital's rule? Because sometimes you can use it and you should not, because it's not great. Here, we definitely can. Square root of x looks like that. It's getting larger and larger and larger as it goes further and further to the right. Natural log of x looks like this. It's getting larger and larger and larger, albeit slowly, as we go further and further to the right. So we are definitely allowed to use L'Hopital's rule because it is an infinity over infinity type. I don't think you need to write this down when you're doing these problems. I'm writing it so you can see that we have this kind of type. But I don't know. I might not write it. I might as a student. I'm not really sure what your teacher wants you to do. Let's use L'Hopital's rule. I do highly recommend writing the L apostrophe H when you're actually using L'Hopital's rule and taking the derivative of the top and the bottom. We must still write the limit as x goes to wherever x is going. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of the natural log of x is 1 over x. And let me point something out here. I'm going to rewrite this just slightly and not as a helpful way as I should. I'm going to write this as 1 over 2 times the square root of x over 1 over x. And if we just tried to evaluate it right now, we might say, well, the numerator is going to 1 over infinity, which is going to 0. And the denominator is going to 1 over infinity, which is going to 0. So you might incorrectly identify this as a 0 over 0. I mean, that's not true. It is a 0 over 0, but it's not something we should use L'Hopital's rule for, because we can simplify this before we try to use L'Hopital's rule. So we definitely should do whatever simplification we can before trying to apply L'Hopital's rule again. So if I do this, I can rewrite this as the limit as x goes to infinity of 1 over 2 root x times x over 1. And then that's going to end up being the limit as x goes to infinity of 1/2 times x divided by the square root of x is the square root of x. And as x goes to infinity, 1/2 times the square root of x also goes to infinity. So technically, this limit doesn't exist because, right, infinity is not a real number, but we would still say the limit is infinity. What this means, or what the way I would interpret this, or let me ask you all. If someone asked you which function is eventually bigger, the square root of x or the natural log of x, which one is bigger? The top one or the bottom one? Well, it has to be, in this case, the top one, because the overall ratio of these two functions is growing infinitely large, which means the top one is much, much larger than the bottom one eventually. Kind of in contrast to the previous example we did over somewhere. Oh, literally on the same page. Right? In this example, the limit ended up being 0, meaning that the bottom function was much, much larger than the top function. If we flip this over, if we'd done this as the limit as x goes to infinity of e to the x over x squared, and we use L'Hopital's rule twice, we have the limit as x goes to infinity of e to the x over 2x. Then we'd have the limit as x goes to infinity of e to the x over 2. And then that's infinity divided by 2, which is infinity. This is telling me that the top function is growing faster than the bottom function. Whereas this is telling me that the bottom function is growing faster than the top function. Which is not always the question, but is often the question that people are asking. Which function is growing faster? Questions so far? Don't hesitate to ask if you have questions. Let's look at some 0 over 0 types. Let's look at a limit that we definitely saw before. The limit as x goes to 0 of sine of x over x. We definitely saw that one before, and it was, still is, a 0 over 0 type. And just to be extra clear here, the reason we have to do this is because 0 over 0 can literally be anything. What's 0 divided by 0? Any number works. Pick whatever you want. I'm going to pick 73. 73 times 0 is 0. 0 minus 0 is 0. Remainder is 0. Great, it worked. But as I think you can all see, the number up there could have been anything. But you can literally make a limit that's a 0 over 0 type that's equal to any value you want. In this example, using L'Hopital's rule, we know the answer is going to be 1, but let's use L'Hopital's rule to show it. The derivative of sine of x is cosine of x. The derivative of x is 1. And if you plug in 0, you get cosine of 0 over 1, which is 1. Could I make one that comes out to be 73? Of course I could. The limit as x goes to 0 of sine of 73x over x. That limit will definitely be 73 because it's still a 0 over 0 type, right? If I plugged in 0, I would get 0 over 0. If we use L'Hopital's rule, the derivative of the top, well, the derivative of sine of some stuff is cosine of the stuff times the derivative of that stuff. The derivative of x is 1. If I plug in 0 now, I get cosine of 73 times 0 times 73, which is 1 times 73, which is 73. So I'm going to say it again. A 0 over 0 limit can end up being any value. It can be any real number, positive, negative, rational, irrational. It can even be infinite or negatively infinite. Although, again, those aren't really existing, but we still write that answer anyway. Let me point out, sometimes using L'Hopital's rule is not the best. Let me show you an example. Let's say the limit as x goes to 0 of sine squared of 3x over 5x squared. This is a 0 over 0 type. And we could totally use L'Hopital's rule. And you watch what happens. So we use L'Hopital's rule. The derivative of the bottom is easy. It's 10x. The derivative of some stuff squared is going to be 2 times my stuff times the derivative of my stuff, which is cosine of 3x times 3. Okay, that's not my favorite, but fine. I'm going to rewrite this as the limit as x goes to 0. 2 times 3 is 6 over 10, or I could actually reduce that to 3 over 5. I've got 3/5 times the fraction sine of 3x cosine of 3x over 10. Oh, sorry, over just x. Apologies there. Sorry about that. That's terrible. It's an x, I promise you. Sorry. Looks awful. And if you try plugging in 0, you're still going to get 0 over 0. Sine of 0 is 0. Cosine of 0 is 1. 0 on the bottom. We got 0 over 0. So we use L'Hopital's rule again. And this is where things get a little bit terrible. We use L'Hopital's rule again. The 3/5 constant is going to hang out in the front. Right? The limit of a constant times a function is just the constant times the limit. And then the derivative of the top is going to be a product rule. So it's going to be cosine of 3x times 3 times the other cosine of 3x plus sine of 3x times the derivative of cosine of 3x, which is negative sine of 3x times 3. This over 1. That one wasn't too bad. And then if you plug in 0, you end up getting 3/5 times cosine of 0 times 3 times cosine of 0 is 1 times 3 times 1. Sine of 0 is 0 over 1. So you end up getting 3/5 times 3, which is 9/5. And that's fine, and that's not too terrible. I will tell you it is exceptionally terrible if the power is higher than 2. The power is 3. It's really like sine cubed of 2x or whatever. It's really, really gross when you get to the third iteration of L'Hopital's rule. Instead, what we could have done is use stuff we did before. We could have used the wish method and said, oh yeah, the limit as x goes to 0 of sine squared of 3x over 5x squared. I'm going to write as the limit as x goes to 0 of sine of 3x over blank times sine of 3x over blank times blank over 5x squared. And then beneath each sine of 3x, I really wish I had a 3x. And then that's easy. The x's here cancel. And you end up getting the limit of that's 1, the limit of that's 1, and 3 times 3 over 5. Oh, look, it's the same answer. And in my opinion, doing it the second way was much easier. So what I'll point out is even though L'Hopital's rule will work sometimes, it's not always the best tool to use. It's still a great tool to use, and often you will want to use it, but occasionally, especially with like a power of sine, it's not really the most excellent thing to use. So just a word of warning. Let's see. Sure. That's tricky. Let's look at something else. Let's say we had the limit. I keep numbers escape me. It's all right. The limit as x goes to 0 of sine of x minus x over x cubed. So if you plug in 0, you definitely are going to get 0 over 0. So I want you all to try doing this one on your own. Use L'Hopital's rule. I think you're going to have to use it like 3 times. Go ahead and get started on that. We should end up getting an answer of negative 1/6 at the end of this problem. Give you another 30 seconds. Okay. So let's see here. So using L'Hopital's rule the first time, I'm going to get the derivative of sine x minus x is cosine of x minus 1 over 3x squared. If I plug in 0, I get 1 minus 1 over 0. So I have a 0 over 0. So I use L'Hopital's rule again. So now taking the derivative of the top, derivative of cosine of x minus 1 is negative sine of x. Derivative of the bottom is 6x. Here you could probably actually switch gears if you wanted to and say it's negative 1/6 times sine x over x. We know the limit as x goes to 0, sine x over x is 1. Or you could use L'Hopital's rule one more time. You get the limit as x goes to 0 of negative cosine of x over 6. And now we can't use L'Hopital's rule anymore because it's not a 0 over 0 type. If you plug in 0, you get negative cosine of 0 over 6, which is negative 1/6. Cool. So if it's already a fraction and it's 0 over 0 or infinity over infinity, this is what we do. But not everything is going to start off as a fraction. For example, you might have something like, something like this. The limit as x approaches 0 from the right of x times natural log of x. It's really, really, really important that you remember what the graph of the natural log of x looks like, because that's how I'm figuring out what's happening with the natural log of x part. So if I think about the graph of the natural log of x for a second, it looks like this. And as x gets closer and closer to 0 from the right-hand side, the graph goes down, 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 down to negative infinity. So this is looking like a 0 times negative infinity. Now, don't get confused by this. I don't really have 0 times infinity or negative infinity. I have a really small number, a number that's really, really close to 0, multiplied by a really, really negatively large number. And the question here is kind of which thing wins? Is the thing that's getting really, really small going to overpower the thing that's getting really, really big, or vice versa? Well, to be able to see that, we have to use L'Hopital's rule. But we can't yet because it's not written in the right form. So we have to make this into a fraction that is either a 0 over 0 or an infinity over infinity type. You typically have two choices. One of them is almost always the wrong choice. One of them is usually the right. So occasionally either way works, but most of the time it's like one way is awful and one way is fine. So here are the ways we could rewrite this. You can either rewrite this as the limit as x goes to 0 from the right of x divided by 1 over natural log of x. This is the wrong way to go. It would be a 0 over 0 type, because the top is going to 0 and 1 over something infinitely large is going to 0 as well. But taking the derivative of 1 over natural log of x is going to be less than excellent. We should make the better choice and do it as a limit as x goes to 0 from the right of the natural log of x over 1 over x. Essentially, you're bringing one of the factors down to the denominator as its reciprocal. And then in this case, I have a negative infinity over infinity type. Natural log of x is going to negative infinity. 1 over x is going to positive infinity. And now we can use L'Hopital's rule. So here, using L'Hopital's rule, I'm going to hit the limit as x goes to 0 from the right of the derivative of the natural log of x, which is 1 over x, over the derivative of 1 over x, which is negative x to the negative 2, or I would write it as negative 1 over x squared. And now we're in a similar situation that we were before. Instead of using L'Hopital's rule again, because we have an infinity over a negative infinity type, we should simplify. We should rewrite this as the limit as x goes to 0 from the right of 1 over x times negative x squared over 1, which is just the limit as x goes to 0 from the right of negative x, which is 0. So the way the words I would use to describe this is the x approached to 0 faster than the natural log of x got big. I know that's not super obvious, but that's kind of how people talk about these things, is that the 0 overpowered the infinity here. And that's why the limit ended up being 0. That won't always happen. Let's look at another example. Let's say we had the limit as x goes to infinity of x cubed times sine of 2 over x cubed. My advice for, actually, well, before we do anything, let's see what we've got. If x is going to infinity, infinity cubed is infinity. 2 over infinity is going to 0, sine of 0 is 0. So again, we have infinity times a 0, or a big thing times a small thing. Typically, it's going to be to your advantage to bring the quote-unquote simpler thing to the denominator. I would say there's one exception to this, but generally the simpler thing here. So I don't want to have like a 1 over sine of 2 over x cubed in the denominator, or even a cosecant of 2x cubed. I definitely don't want x cubed over 1 over sine of 2 over x cubed, or even if you prefer, x cubed over cosecant of 2 over x cubed. It's going to be just kind of, right, the derivative of cosecant of 2 over x cubed is going to be not very nice. That might actually end up working out, but I don't want to deal with the harder version. I would much rather write this as the limit as x goes to infinity of sine of 2 over x cubed over the reciprocal of x cubed. And I probably would rewrite this in a way that made it easier to differentiate the top thing and the bottom thing. I would probably rewrite this as the limit as x goes to infinity of sine of 2 times x to the negative third over x to the negative third. It's still a 0 over 0 type, right? It is a 0 over 0 type. Just as a, right, this is a sine of 0 goes to 0, 1 over infinity goes to 0. They're both going to 0. So it's definitely a 0 over 0 type. And if we use L'Hopital's rule, we still have a limit. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. And the derivative of 2x to the negative third is negative 6x to the negative fourth. On the bottom, the derivative of x to the negative third is negative 3x to the negative fourth. And I can definitely cancel some stuff. Those x to the negative fourths definitely cancel out. So I would probably then rewrite this as the limit as x goes to infinity of cosine of 2 over x cubed. And then negative 6x to the negative fourth divided by negative 3x to the negative fourth is just 2. And then you can take the limit. As x goes to infinity, 2 over x cubed goes to 0. And cosine of 0 times 2 ends up being 1 times 2. So here the infinity and the 0 kind of pushed and pulled against each other, and we came out somewhere in the middle at 2. Kind of interesting. So one type of indeterminate form that comes up frequently is an infinity times a 0. Or a 0 times a negative infinity is also a possible thing. There are other types of indeterminate forms. For example, so let me just list them real quickly here for you so you'll know what they look like. 0 over 0 and infinity over infinity are the ones that we like the most, because we can just use L'Hopital's rule. 0 times infinity is also an indeterminate form. So is infinity minus infinity 1 to the infinity, 0 to the 0, infinity to the 0. 0 to the 0 is not 1 all the time. It's often 1. But again, all of these are forms that can be anything. These ones specifically are the exponential ones. And they almost always require doing something with a natural log. Which we'll get to in a minute. Let's look at, let's look at one more example. We need more page. So these are the various indeterminate forms. And I'm fairly confident that this list is exhaustive. I think these are all of them. I don't think there's anything that's missing here. I guess it should be more inclusive here. This should be a plus or minus infinity over a plus or minus infinity. This should be a 0 times a plus or minus infinity. These other ones should not be plus or minus. These other ones are specifically positive infinity minus positive infinity, 1 to the positive infinity, 0 to the 0, positive infinity to the 0. Although you can probably get a negative in some of those. All right, let's look at something kind of weird. The limit as x goes to infinity of, I had something in mind and now I've forgotten it. Where'd you go? You're not there. Okay, that's fine. Sure. Sorry, I had this example that was in my head and now it's completely gone. Well, fine, we'll skip it. I'll come back to it in a minute. Let's try this one instead. Let's try, yeah, oh yeah, this is a good one. The limit as x goes to infinity of 1 plus 1 over x to the x. Which may or may not look familiar. So this is an exponential form. It's also indeterminate because if you let x go to infinity, you essentially got a 1 plus 0 to the infinitieth power, or a 1 to the infinity. Now I want to make it clear. We don't have 1 times 1 times 1 times 1 times 1 times 1 forever. We have a number that is really, really, really close to 1. Times itself again and again and again and again, which means it might grow beyond 1 because it's really not exactly 1, it's a tiny bit bigger than 1. And that is really important because if it was exactly 1, then you'd be like, yeah, the limit's going to be 1. But since it's a tiny bit different than 1, it can be anything. So let's see what happens here. There's 2 ways of doing this, and I should actually ask you all. For those of you that have seen this in your class, has your professor just taken the natural log of the expression, or have they done like e to the natural log of the expression? Or does it not? Sure. Okay. I'll show you both ways. I would say I'm probably more prone to do it this way. I would like to write my limit as x goes to infinity of 1 plus 1 over x to the x as being equal to the limit as x goes to infinity of e to the natural log of the same expression. So they haven't really changed anything. E to the natural log of some stuff is just the stuff. But then, and I would say this process is very similar, but not the same as when we do logarithmic differentiation. We take the natural log of both sides of an equation, and then we bring down the power so that we can differentiate both sides. We're employing a similar trick here in that we're taking the natural log of this expression, but we really need to do e to the natural log, so it's still the same, so that we can bring this exponent down out of the exponent. So I'm going to rewrite this as the limit as x goes to infinity of e to the x times the natural log of 1 plus 1 over x. And now in your exponent, you have an infinity times a 0. X is going to infinity. Natural log of 1 plus 1 over x, well, 1 over x is going to 0. 1 plus 0 is 1, and the natural log of 1 is 0. So you have an infinity times 0, which we know is also an indeterminate form. So we're going to rewrite it in a way that is fractional. Sorry, I just bumped the camera. It's terrible. Get back, okay, maybe, sure, okay, sorry. So I'm gonna rewrite this as the limit, as x goes to infinity of e to the, okay, of the two things, the x and the natural log of 1 plus 1 over x, one of those is definitely the simpler thing to put in the denominator. The x should come down to the denominator as its reciprocal, 1 over x. So we're gonna write this as the natural log of 1 plus 1 over x over 1 over x. And now that exponent is in an indeterminate form that we can use L'Hopital's rule on. It's a 0 over 0 form. I don't think you need to write this next part, but some people prefer to say that we pass the limit through the exponential. Way back when we talked about limits in the beginning of the quarter, there was a theorem about how the limit of a continuous function is like the function of the limit of the inside part. Or essentially you can say that this is equal to e to the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. Most people skip writing that. And they just say, oh, we know that that works that way. We're just going to say apply L'Hopital's rule. The limit's still out in front. The e to the whatever is out there. And then we're applying L'Hopital's rule to the exponent here. So you got a 0 over 0 type. We're going to take the derivative of the top, which is 1 over 1 plus 1 over x, times the derivative of 1 over x, which is negative 1 over x squared, over the derivative of 1 over x, which is also negative 1 over x squared. And very conveniently, the negative 1 over x squared cancel out. So you're left with the limit as x goes to infinity of e to the 1 over 1 plus 1 over x. The 1 over x is going to go to 0 as x goes to infinity. So we're left with e to the 1 over 1, which is e. And you might remember this being the way we defined e way back when. You might not, though, because we might have done it slightly differently. We might have defined e to be the limit as x approaches 0 of 1 plus x to the 1 over x. I would encourage all of you on your own at some point to do this limit the same sort of way, and you should also end up getting e to the 1. So a lot of these exponential types require this process, where you do e to the natural log of your thing, you manipulate the thing until it looks like a fraction that's either a 0 over 0 or an infinity over infinity, and then you apply L'Hopital's rule. Let's look at another example. This definitely does this specific type of limit, I will say, actually this specific type of limit, I will say, does come back in 21C when you're doing some stuff with series. So it definitely is right. We're not just doing it for the sake of doing it. It actually, right, we do use these things later on. Let's do one more. Yeah, let's do one like that. Let's say we want to find the limit as x approaches 0 of 1 plus 3x to the 5 over x. All right. So again, we're going to do this. So let me actually show you the other way of doing this. Instead of doing the e to the natural log, I'm going to do this instead. I'm going to say this is equal to the limit as x goes to 0 of e to the natural log of 1 plus 3x to the 5 over x. And then I am going to pass the limit through. I'm going to say this is equal to e to the limit as x goes to 0 of the natural log of 1 plus 3x to the 5 over x. And then what we're going to do is we're going to just figure out what that top part is. So we're going to say, okay, great. We're going to fill in the box with whatever the limit as x goes to 0 of the natural log of 1 plus 3x to the 5 over x is. Or as some people like to kind of present it, we take the natural log of our expression, we deal with that, and then at the end of the day, whatever our answer is, our real answer is actually e to that answer. So let's see what we get. Again, the reason for taking the natural log here is so that we can bring down the exponent. Now, if I was being more careful about this, I would do this in one step, because I would realize that the 5 over x, the x I can just think of as being in my denominator. So I could really write this as the limit as x goes to 0 of 5 times the natural log of 1 plus 3x divided by x. There is absolutely no reason to make the denominator x over 5. That 5 can be wherever we want to leave it, and I might as well leave it in the place that's easiest to write it. The only thing that matters here is that the top and the bottom are both going to either 0 over 0 or infinity over infinity. And here it should be 0 over 0. Certainly the denominator is going to 0. And the numerator, yep, if x is going to 0, 1 plus 0 is 1. Natural log of 1 is 0. So we definitely have a 0 over 0 type. Do make sure you check, at least mentally, to see that you actually have something you use L'Hopital's rule for, because occasionally someone's going to throw a limit at you where you think you can use L'Hopital's rule and you actually can't, because it's not a 0 over 0. It's like a non-0 over 0. So I'll show you an example of that in a second here. Well, so then, but using L'Hopital's rule here, we're going to get the limit as x goes to 0 of the derivative of the top. Well, the derivative of the bottom is 1. The derivative of the top is 5 times 1 over your stuff times the derivative of your stuff. My God, I was watching the new Mean Girls movie last night, which is a musical, but they're in a math class some of the time. And at one point, the teacher said, solve an equation. I'm like, that's not an equation. That's an expression. Really, it bothered me. I was like, they should be better at their math language there. And some of the limits, I was like, I don't know about those limits. They look like they're a little dicey. Anyway, I know that's not the point of the movie, but you should have your facts straight. Anyway, evaluating this limit, which does exist, it's going to be 5 times 1 over 1 plus 0 times 3, which is just 5 times 1 times 3, which is 15. And then it's really, really, really important that we don't stop there. That's not our final answer. Our final answer is e to the 15th power. This is why I don't particularly prefer to do it this way, because I feel like it's easy to forget that last bit and put your number back in the exponent of e. But you're welcome to do it either way you want. Just if you do it this way, make sure you remember to take that final number and plug it back in as your e to the thing. Let's look at a couple more. Yeah, a couple more. Sure. Let's do, yeah, this one. Actually, let's do that. I skipped one back there. Let's go back to it. Yeah, let's do this one. The limit x goes to infinity of x to the 1 over the natural log of x. Yeesh. All right, so this is an example of an infinity to the 0th power. X is going to infinity, and the exponent is going to 1 over infinity, which is 0. And this is an indeterminate form, which I know is kind of weird, but it isn't. Like the infinity to the zeros always feel strange to me. They just do. I don't know why. This one is especially contrived to come out kind of atypically. So let's do the thing. Let's rewrite it as, right, we can't, so I want to make it really clear, we can't just throw L'Hopital's rule at it yet. It's not a fraction. Sure, there is a fraction in there, but it's not a 0 over 0 or infinity over infinity. So until you have that fraction that is 0 over 0 or infinity over infinity, we are not permitted to use L'Hopital's rule. So here, limit as x goes to infinity. I'm going to rewrite this as e to the natural log of the stuff. And then I'm gonna bring the 1 over natural log of x down in front. And this is where this problem, I think, is extra funky. Because it's gonna be e to the 1 over natural log of x times natural log of x. What's 1 over natural log of x times natural log of x? This is the limit as x goes to infinity of e to the 1. Well, that's a constant. So it's just e. I didn't even have to use L'Hopital's rule here. I will say this problem is somewhat unique in that sense, because normally these problems do require L'Hopital's rule. This function, this x to the 1 over natural log of x, is kind of weird. This, and I'll point out, because I do think it's kind of worth mentioning here. X to the 1 over natural log of x is always equal to e. It's strange, I know. But the domain is there. In fact, let's graph it. It's kind of cool. I just want to show you all so you really believe me. And I should be smarter about this. Yeah. Got some Desmos going on. Oh, yeah. So if I graph this, y equal to x to the power of 1 divided by natural log of x, check that out. It's always e when it's defined. Right? Here's just so you can compare. Here's y equal to e. Oh yeah, they're the same. Except this one isn't defined when x is negative or 0, and this one is. Kind of wild. Kind of weird. You probably won't see this function, but it's kind of interesting, I think. Let's look at a more realistic example of an infinity to the 0 type of L'Hopital's rule question. Which I will say most of the infinity to the 0 types and 0 to the 0 types do end up equaling 1. Not all of them, as we just saw an example of one that was not equal to 1, but most of the time they do. Here's an example. Let's say, do I have this example here? Sure. One second. Sorry. Gosh, lost my cursor. So I'll make sure I'm doing the example I actually want to do. No, not you. Yeah, you. Cool. So let's say you want to do the limit as x approaches 0 from the right of sine of x to the, that's not what I, sorry, that's actually not what I want. Oh, well, we'll do this one first. That's fine. Sine of x to the 1 over x. Which is actually not an infinity to the 0 form. It's a 0 to the infinity form. Now, what I want to point out here, that's not an indeterminate form. Let me say it this way. If you had a number that was really, really small, certainly less than 1, and you multiplied it by itself over and over and over and over and over again, would it get bigger or smaller? Smaller, right? 1/2 times 1/2 times 1/2 times 1/2 over and over and over again. It's really, really small. So if you have a number that's getting close to 0, raised to an ever increasing power, it means you're multiplying a number that's really small by itself over and over again. You're getting closer and closer to 0. So technically, you don't really need to use L'Hopital's rule here. You still can look at it this way. If I want to use L'Hopital's rule, I certainly could. So the limit as x goes to 0 from the right. Well, I should say, I might not end up using L'Hopital's rule. I'm certainly going to rewrite it. Yeah, sure. Okay. So I've got e to the natural log of sine of x to the 1 over x. I'm going to bring the 1 over x down in front. The limit as x goes to 0 from the right of e to the, now let's be smart about this. Instead of writing it as 1 over x times the natural log of sine of x, let's write it as the natural log of sine of x over x. And here's what I'm going to point out, that we really actually don't have an indeterminate form. So this is right, the step I skipped here was writing it as e to the 1 over x times the natural log of sine of x. Sine of x is going to 0, right? Sine of 0 is 0. Natural log of 0 goes where? Natural log of 1 is 0. Natural log is 0. Think about the graph of the natural log. Yeah, negative infinity. Super duper. I can't stress enough to deal with the natural log comes up a lot in these limits. You have to know what happens to natural log as you either get closer to 0, down to negative infinity, or get bigger and bigger, up to positive. And the easiest way for me to do that is just to remember what the graph looks like. I know I have a vertical asymptote as I go closer to 0. I know I get larger and larger as I go further to the right. But really just drawing the graph, I'm like, oh yeah, the graph. The graph does that. Cool. It's down to negative. So here's what I've got. On top, for just the exponent here, I've got a negative infinity on top. And on the bottom, I have a 0. And I will say that is not an indeterminate form. It's not 0 over 0. It's not infinity over infinity. A really, really negatively big number divided by a super tiny positive number is really negatively big. Negative 1 billion divided by 1/2 is negative 2 billion. Negative 3 billion divided by 0.00001 is a huge negative number. But we don't have to do any L'Hopital's ruling here to know that. We can be like, oh yeah, that's a negative big number. So we're going to get here is, sorry, I've kind of screwed myself over as far as where I've written this. This is going to be the limit as x goes to 0 from the right. E to the natural log of sine of x over x is essentially just e to the negative infinity, which is 1 over e to the positive infinity, which is 1 over a really big number, which is 0. Which we already knew, because we said we had this really, really small number multiplied by itself a bunch of times, and it stayed really small. So let's look at a better example. What I really wanted was an infinity to the 0, not a 0 to the infinity. I will point out that really kind of emphasizes the point of you really have to make sure you can use L'Hopital's rule before you just throw out a problem. If you try to use L'Hopital's rule here, you would have gotten like, right, you would have taken the derivative of the top and the derivative of the bottom, you would have gotten like 1 over sine times cosine, and then the x and the 1 on the bottom. It would have turned out really, really weird. Probably incorrect. So let's look at something a little bit more normal, like the limit as x approaches 0 from the right of 1 over x to the x. And this is certainly an infinity to the 0th power type. And I'm pretty sure the answer is going to end up being 1. Let's try and make it a little bit different. Let's see if we can make the answer not be 1 by making that a 4 over x instead of a 1 over x. I really don't think it's going to make a difference, but let's find out. All right, everybody should write down the first step. I want you all to rewrite this as the limit as x goes to 0 from the right of e to the something. You all should write what you have up here. You should have e to the natural log of the original expression, 4 over x to the x. And then we're going to bring the x down. That's the whole reason we did it. It's going to be e to the x times the natural log of 4x. Here, I do have to do more work to re-express it, right? Because I don't have a fraction yet that is an indeterminate form. So I'm going to rewrite this once again as the limit as x goes to 0 from the right of e to the natural log of 4 over x over the reciprocal of x, which is 1 over x. And now I think I have an indeterminate form, but let's check to be sure. If x is going to 0 from the right, 4 over x is getting infinitely large, and the natural log of infinity is infinity. 1 over x is also getting infinitely large. So yeah, we definitely have this top part here, this exponent being an infinity over infinity type. So we are permitted to use L'Hopital's rule. we're gonna get the limit is x. Oh, I forgot. Well, I didn't really forget, but I would like to have written the L apostrophe H to show that I'm using L'Hopital's rule in this step. E to the, all right. The derivative of the top is, the derivative of the top. I don't want to do that. I should be smarter here. I really should be smarter here. What I should do, instead of doing the natural log of 4 over x, I should use a logarithm rule. So before I use L'Hopital's rule, sorry, I know I wrote that up here, but I'm gonna skip a step here, or not skip, I'm gonna come back to it. I could write this as, yeah, I was like, I could do this. The natural log of 4 minus the natural log of x all over 1 over x. Totally valid. Still an infinity over infinity type, because now when x goes to 0, natural log of 0 goes to negative infinity, and minus infinity, still going to infinity on top, right? Simplifying something, but not really changing it shouldn't change what the limit type is. And now we can go up here and be like, okay, the derivative of the top is going to be 0 minus the derivative of the natural log of x, which is 1 over x. And the derivative of the bottom, the derivative of 1 over x is negative 1 over x squared. I will say the derivative of 1 over x comes up often enough that you should just get used to saying, oh yeah, the derivative of 1 over x is negative 1 over x squared. All right, simplifying this, we have the limit as x goes to 0 from the right of e to the negative 1 over x times negative x squared over 1 simplifies to just x. So you've got the limit as x goes to 0 from the right of e to the x, which becomes e to the 0, which is 1. So it is pretty true that most of the time, the infinity to the 0 type or the 0 to the 0 type does end up having a limiting value of 1. Not 100% of the time, most of the time. I would encourage all of you on your own to show that the limit as x approaches 0 from the right of x to the x, which is a 0 to the 0 type, also ends up being 1. Through the same sort of process. What time is it? Okay, we got a few minutes left. So a couple more things. Well, yeah, let's do that one. What about the limit as x goes to negative infinity of x cubed times e to the x? So here's what I actually want to point out with this problem. I've seen people do this problem so wrong. I have to say something. Not that I've seen any of you do it wrong, but in the past, I've seen people be like, oh yeah, I need to use L'Hopital's rule because it is indeterminate. This is a negative infinity times an e to the negative infinity, which is a 0. So it's definitely an infinity times 0 type. And here's the work I've seen done that has just killed my soul. I've seen people do this. The limit as x goes to negative infinity of x cubed e to the x is equal to the limit. Don't write this down. As x goes to negative infinity of 3x squared times e to the x plus x cubed times e to the x. Just took the derivative, which is totally incorrect. But I have to say it because I've seen so many students do it in the past that I want to make sure that you know that if you're trying to take a limit, we can't just take the derivative of the expression. We can only start taking derivatives when we're applying L'Hopital's rule. And we can only apply L'Hopital's rule to what kinds of things? I'm looking for an F word. What kinds of things can I use L'Hopital's rule for that starts with an F and ends with an actions? Fractions, specifically of a 0 over 0 or infinity over infinity. So we don't have a fraction yet, right? So in this case, and this is the one case I was kind of alluding to earlier, in this example, you definitely want to bring the e to the x down to the bottom. So it's really, really better to rewrite this limit as x cubed over e to the, I'll write it as 1 over e to the x, but then I would really write it as the limit as x goes to negative infinity of x cubed over e to the negative x. If you try going the other way, if you try writing it as the limit as x goes to negative infinity of e to the x of over 1 over x cubed, which becomes the limit as x goes to negative infinity of e to the x over x to the negative third. The problem here is that when you take the derivative of e to the x, it's just going to say e to the x every time. When you take the derivative of x to the negative third, the power is going to get more negative every time you take the derivative. And you're not going to get closer to any sort of resolution. Whereas when you do it this way, you start using L'Hopital's rule, the power of the derivative of x to the third, the power is going to get lesser and get closer to 0. On top, the derivative is 3x squared. On the bottom, the derivative is negative e to the negative x. Still an infinity over infinity type. The top, here the top's going to negative infinity, here the bottom's going to infinity. So we do it again. Sorry, I meant to point here. Here the top's going to infinity, the bottom's going to negative. So we take the derivative of the top, which is 6x. The derivative of the bottom is positive e to the negative x. The top's going to negative infinity, the bottom's going to positive infinity. And finally, one more time, the derivative of the top is 6. The derivative of the bottom is negative e to the negative x. And now we no longer have a 0 over 0 or infinity over infinity type. The top is going to 6, and the bottom is going to negative infinity, which is going to give me 0. Which shouldn't surprise us, because we are used to seeing an exponential function overpower a polynomial function. It's almost always going to be the case. Let's see, what else to say here? Sure. Or something. Oh yeah, that. So what about, say, the limit as x approaches infinity of the square root of x squared plus 9x minus the square root of x squared plus 4x. Definitely an infinity minus infinity type. It's kind of terrible looking. Infinity minus infinity could be anything. It could be infinity. It could be 0. It could be negative infinity. It could be 5. It could be 1. Any answer is, I know I've said this a lot, but I really just want to stress again and again and again. For indeterminate forms, you can get any possible numerical or infinite or negatively infinite answer. Anything is fair game, which means we have to do work. You can't just say, oh, it's something. Here, we need to get a fraction so we can think about maybe using L'Hopital's rule. I will fully admit, I'm not 100% sure we actually end up getting to use L'Hopital's rule here. But either way, I'm going to start by multiplying the top and bottom of this fraction by the conjugate. Because that's the only thing I can think to do. Let's see what happens. When we multiply out the top, the usual thing happens where they're conjugate. So you get the first thing squared, which is x squared plus 9x, minus the second thing squared, which is x squared plus 4x. On the bottom, I've got the square root of x squared plus 9x plus the square root of x squared plus 4x. Now, yeah. Simplify on the top a little bit. I've got the limit as x goes to infinity of x squared minus x squared cancels. 9x minus 4x is 5x over the square root of x squared plus 9x plus the square root of x squared plus 4x. And I will tell you, I'm really apprehensive about trying to apply L'Hopital's rule here. I certainly can, right? The top is going to infinity. The bottom is going to infinity plus infinity, which is infinity. but I'm worried that applying L'Hopital's rule here is going to be really, really gross. But let's try it anyway. So applying L'Hopital's rule, the derivative of the top is 5. And I'm imagining each of these things as something to the 1/2. So the derivative of x squared plus 9x to the 1/2 is going to be 1/2 times x squared plus 9x to the negative 1/2 times 2x plus 9. That seems terrible. And then same thing here, the derivative of that's going to be 1/2 times x squared plus 4x to the negative 1/2 times 2x plus 4. Ooh, that does not seem better. Take a look at what if I rewrite this one more time, I've got the limit as x goes to infinity of yeesh. I'm going to multiply the top and bottom by 2 to get rid of those 1/2s. So I have 10 on top. And then here I have 2x plus 9 over the square root of x squared plus 9x. And here I have 2x plus 4 over the square root of x squared plus 4x. That seems really bad. Those both look like things I would have to use L'Hopital's rule on again, which seems terrible. This is an example, although it's not a great example, of a function where if you keep applying L'Hopital's rule, you kind of just undo what you've done before. Yeah, we have enough time. Let me finish this problem the right way and then show you a better example of what I'm trying to say. So the better way to do this problem is actually not to use L'Hopital's rule. The trick here is to employ a previous tactic and say, well, the limit as x approaches infinity of 5x over, and the bottom, what I'm going to do is I'm going to factor out an x squared from inside each of the square roots. I'm going to have the square root of x squared times 1 plus 9 over x plus the square root of x squared times 1 plus 4 over x. What's the square root of x squared? Well, technically it's the absolute value of x, but since x is going to infinity, we can just say it's x. So we're going to have x times the square root of 1 plus 9 over x plus x times the square root of 1 plus 4 over x. And then this x divided by that x is 1. So then we're left with something we can evaluate. The limit as x goes to infinity of 5 over the square root of 1 plus 9 over x plus the square root of 1 plus 4 over x. The 9 over x goes to 0. The 4 over x goes to 0. You're left with 5 over 1 plus 1, which is 5 over 2. So in this strange example, the first infinity is 5/2 bigger than the second infinity, which I know sounds like kind of a silly thing to say, but that's what we're getting. We're getting that this minus that ends up equaling 5/2. So forever and ever and ever, this car driving at this position will be 5/2 of a mile further than that car driving at that position. Kind of weird. Let me say a little bit more about this because it's good a place as any to wrap things up. The thing I was trying to point out here, which is kind of weird, is if you have something like the following, the limit as x goes to infinity of, let me think for a second here. Yeah, that'll work out. Sure, let's say 2x over the square root of x squared plus 1. Totally infinity over infinity type. Let's see what happens if we apply L'Hopital's rule. So the derivative of the top is going to be 2. The derivative of the bottom, I have something to the 1/2. I'm going to get 1/2 times my stuff to the negative 1/2 times the derivative of my stuff. Okay, but look at what this ends up being. This ends up being the limit as x goes to infinity of, let's see, the 2 can cancel with that 2 there. We've got 1 over 1/2 times 1 over the square root of x squared plus 1 times x. Or flipping and multiplying, I've got the limit as x goes to infinity of 2 times the square root of x squared plus 1 over x. it kind of looks like all I ended up doing was flipping my fraction over. And the real bad news is if I do L'Hopital's rule again, I'm going to end up exactly where I started. That's not helpful. It didn't do anything for me. So this is an example of a problem where you can apply L'Hopital's rule, but it doesn't help. It doesn't get you anywhere. Sometimes L'Hopital's rule is not helpful, even though it is allowed to be applied. So here you would deal with this one the same way we dealt with that previous one. You'd say, oh, I'm just going to view this as the limit as x goes to infinity of 2x divided by the square root of x squared times 1 plus 1 over x squared. And then bring out the x squared as an x. And you have 2x over x times the square root of 1 plus 1 over x squared. The x's cancel, and you're left with 2 over 1 plus 0. Just 2. Yeah.
Can you explain why in this problem we did 1 over x squared and then previously did 9 over x and 4?
Oh, so what I'm doing here is I'm factoring out the x squared. So in the previous problem, I didn't have just a 9, I had a 9x. So over here, right, when I was doing this, I had an x squared plus 9x. So when I'm factoring out the x squared, I'm getting x squared times 1 plus 9 over x, because when I distribute that back in, I'm getting x squared plus x squared times 9 over x, which is equal to x squared plus 9x. That's why I'm getting that. So it's just, each time I'm just factoring out the x squared, I just have a different thing inside my expression, my square root. So yeah, L'Hopital's rule is great, but it can't always be applied. Yeah, I think that's all I have to say. All right, Thursday, we'll review. I think we'll start off by kind of probably going through the syllabus and talking about like hitting the highlights, being like limit definition, continuity, taking derivatives, product rule, chain rule, quotient rule, trig derivatives, exponential, log, optimization, related rates, implicit, graphing, L'Hopital. I feel like that's most of the things. You're probably missing 1 or 2 things, but that's also you should be aware of what kind of things will be on your final, right? Like, is your teacher going to ask you a limit definition of the derivative question? Probably not, but they might have said like they are or are not going to. So it is definitely worth looking at what they've written about your final, because sometimes people will be very explicit. They're like, yeah, I'm going to ask you these kind of things. I'm not going to ask you limit definition of the derivative. Usually it gets left off the final because we feel like we've already covered it in the midterm, but sometimes people ask it. Or is there going to be a delta epsilon proof on your final? Probably not, but it's good to know whether or not these things are going to show up. So definitely look at whatever your teacher's written about your final exam. I will try to look as well to see if I can discern anything, but you should be aware of what you're expected to be responsible for before going into your final. All right, I'll see you all on Thursday. Oops, that's not what I mean to do.